In this video, we're going to go over scalars and vectors. Now, because this is the first of the video notes that we're doing, I'm just going to try to guide you along. You will definitely need a calculator, preferably a scientific calculator, because we will be doing some calculations. And during those calculations, I encourage you to pause the video, try it out yourself, and make sure that you get the same results that I do. And there's going to be a lot of pausing the video in order to be copying down notes. So just get used to that. That's what we call active note taking, where you're just not watching the video, just trying to absorb it all, right? Because you'll be taking down the notes. And yeah, let's get started. So our very first lesson, scalars and vectors. So I want to start us off with a couple of definitions. Okay, so at this moment, just pause the video right now, jot down the definitions, okay? And we're gonna go over the definitions in a bit more detail, all right? So the vector is a quantity with both magnitude and direction. And of course, all this becomes a little bit easier with some examples. Scalar is just a quantity with just magnitude, okay? And the magnitude is a size or quantity of things. So once again, it's really easier with the examples. So here's a table of the scalars and vectors. Okay, so one thing I want to point out, we will be using the metric system. Right, so we're not going to be using feet or miles or yards, but rather meters and kilometers. Okay, so a scalar definition is 10 meters per second. But remember, the difference between a scalar and a vector is that a vector has direction. So we could write that instead as 10 meters per second north, right? And that north makes it a vector. Another example of a scalar would be 20 miles, okay? And the vector version would be 20 miles west. Once again, that direction helps. And the very last example is my way of showing that not all scalars can be turned into vectors if you just add a direction. So for stuff like time, 10 seconds, adding a direction doesn't make sense. Or something like temperature, like outside, it's like 98 degrees Fahrenheit, right? That wouldn't make any sense if we said 98 degrees Fahrenheit to the left, right? So having a direction makes it a vector, but only when it makes sense. All right, so let's take a look at this example here, 10 meters north. Let's break this down with our definitions. So here we have this 10, okay? So this 10 is what we're going to call the magnitude. So it's how big something is, how big or small. And then next to it, we have the meters. So these meters, this is the units, so that we know exactly what we're talking about when we're communicating with each other, right? So meters is a unit of distance, and the last one is north, and this is our direction. So when you have both the magnitude and the direction, remember that gives us a vector. If we just had the magnitude and that's it, right? Magnitude of the units, and we always need to have units that will give us just the scalar, all right? Okay, so next up, we're going to go into how we represent vectors in class. So we'll be doing a lot of drawing and model making and creating like our own graphics in physics. And the best way to talk about vectors is the use of arrows. Now remember, vectors is just a generic term. And so with each unit, we have different kinds of vectors. For example, in a previous, we said that there's like 10 meters per second north, right? So that's a variable for speed or how fast something is moving, which is different from, let's say, just 10 meters, which is a unit of distance, okay? And so with each unit, we're going to have different kinds of vectors, but all vectors can be represented with arrowheads. Now, arrows and arrowheads are used because the length of the arrow is used for magnitude. So here and here. So let's call this vector A, and this is vector B. Okay, and just a quick little side note, whenever we write vectors, there's two ways of representing this. I'm going to show you one way. If this is called vector A, usually we put an arrowhead on top of the letter. So that's vector A, and this is vector B. Okay, and this is a way for us to communicate, knowing that direction matters. So let's talk about the magnitude. So if we take a look at the magnitude of A, it's a lot smaller than the magnitude of B, right? And so if I were to ask you, hey, which one of these is, let's say, 12 meters, and which one of these is, let's say, I don't know, 2 meters, okay? We can say that A is the 2-meter one because it has a smaller length arrow versus the 12-meter one, which has a longer arrow, okay? And in order to make these vectors, we would add the words to the right, okay, or even east, thus making a vector. Okay, denoting a vector. So at this point, I'm going to be writing on the screen, and I highly encourage you to write along with me and pause the video and go back if I'm talking too fast or if you need to just catch up. So the first thing I want us to do is to draw a Cartesian plane. So let's draw a Cartesian plane, like so. All right, and we're going to draw a vector right in the middle of it. Let's make this nice and bold. There we go. Here. Okay. So we have this vector, and we're going to call this vector v. So in order to describe vector v, I'm going to write over here the following. You can probably figure out what all this means. I'm going to say this is 12, comma 9. Okay, so because this is a Cartesian coordinate, like the xy coordinate plane, okay, you're probably thinking, well, that 12 represents the x-axis, and that 9 represents the y-axis, and you'd be correct. Okay, so this tells you how far along the x-axis we go. So in this case, it's 12. So let's visually represent that here. Oops. So from here to here are 12 units, and then our rise would be the 9. And so let's go from here to here. This will be the 9 units. Okay, so this is a way in the Cartesian plane of describing this vector. Now, in order to determine the actual magnitude of the vector, we do have to use our calculators. So bring out your calculators, and let's talk about our the triangle that we'll be using a lot in this course. This is the right triangle. All right, so if we have a right triangle of 12 and 9, and this right here, this is our hypotenuse, okay, and this is our v. In order to actually find the hypotenuse, knowing that this is the angle, this is the right angle and that's the angle, we have to use the Pythagorean theorem, okay? Now, we'll be using the Pythagorean theorem a lot in this course to find the unknown side of any triangle, okay? Because most of our triangles will be right triangles. So knowing the Pythagorean theorem is a squared plus b squared is equal to c squared, we can represent the a and the b and the c with the triangle above. So this will be 12 squared plus 9 squared is equal to v squared, right? And we can see using some algebra, we got 12 squared plus 9 squared, and we get the answer of, let's see, so this would be 15? Yeah, there we go, right? So you could probably put that into the calculator and figure that out, but we have the vector, and that's the magnitude of 15. So what I'm going to do next is I'm going to show you how we can denote magnitude or scalars, right? So we can say V has a magnitude, right? You see those double brackets that we put next to it. That's to show us that we're looking at scalars of 15 units. Now, this vector has a direction, and that direction is denoted by the angle. So is direction. And we do have to use trigonometry in order to figure out that angle right there. So let's get some trig. Now, we are going to be using SOHCAHTOA a lot. So in case you're wondering, the S in so this is if you want to use sine, you need to make sure you have the opposite side and the hypotenuse side. If we want to use ka, or the cosine function, we use the adjacent side and the hypotenuse side. And if we use TOA, this is the tangent, which means that we're using the opposite and the adjacent. Okay, so just so you know, right here, these are the trig functions, and what they do is they show you the ratio of the sides of a triangle. Okay, and in order to use those individual trig functions, you need to have either or both of these sides of the triangle. Okay, so for example, in our 12, 9 V triangle, we have the opposite of the angle, which is 9. So we have the O, and we have this 12, which is the A. Okay, so because we have the O and the A, we can use the tangent. So the angle is equal to the inverse tangent of TOA, so 9 over 12, and that should give us, I should write this one down, 36.8 degrees. Okay, so make sure you pause the video, go to your graphing calculators, and see if you, when you plug this function in to your calculators, that you get 36.8 degrees. All right, so that's one way of writing vectors. I'm going to show you another way of writing vectors. Okay, this is what we call the hat notation. Well, I call it the hat notation. So let's do it. So let's say, so let me give you the long form, right? So this is the official formula. So R is equal to A I hat plus B J hat plus C K hat. Okay, and so those, let's go over each part of that formula individually. Okay, so R is the vector. Okay, A, B, and C, those are the magnitudes. And the I hat, the J hat, and the K hat, those are the directions. Okay, and we use the IJK when we're talking about 3D space. But a lot of the physics that we do, we use a 2D space. Okay, but our reality, we live in a 3D world. So you might see I hat, J hat, and K hat. All right. So in this next example, we'll be working in a 2D space, but just so you know, if we were working in a 3D space, we will include the C and the K. Okay. All right. So let's create a Cartesian plane. Okay, so let's do the same example that we did before, where it was the 12 and the 9. So we're going to create a vector out here, right? And I'm going to say this right here. This was the 12, and this right here, this was the 9. And we call this vector V, I believe, right? Okay, so in order to write this out, we would say V, okay? So we can use that arrow notation, or even could put a hat on top of it. Both are fine. I personally use a lot of the arrows myself, okay? Is represented as 12, so remember that's the magnitude, I hat plus 9 J hat. Okay, so the I, J, and the K represents the X, Y, and Z axis. Right. So here, this is the 12 in the I hat direction, or the X direction, and here we have 9, and this is in the J direction, or the Y direction. And with all that combined, that tells us what V actually is. All right. So we could even write this as V is equal to 12 comma 9, right? We could write it like we did before. We could write it as V is equal to 12 I hat plus 9 J hat, right? Or we can even say that the magnitude of this, what do we find it? It was 15, right? So there's a lot of different ways of describing that one arrow right there. All right, well, that's the end of the video. In the next one, we're going to go over how to add vectors. I'll see you later. Bye-bye.